Hello and welcome to Engineering Problem and Solution. Today we are going to focus on the topic which is known as transient current analysis for RC circuit, and it is one of the very interesting topic for any electrical and electronics engineering. So what I'm going to do is I'm going to draw the circuit which contain step voltage, resistance, and the capacitor. So let's draw the circuit with the step voltage. So we have a step voltage here, and then we have a resistor here, and then we have a capacitor here, and we are trying to write this as a resistors R, capacitor C, and then step voltage which is applied. Step voltage is applied Vt of V0 voltage. So what we have to do here, we have to find the transient current, which is IT, and that's the expression we need to find. Once we draw the current which is on clockwise direction, we'll get plus minus here, plus minus here. We are going to get VR here and VC here. Right. Let's also represent there is initial condition. So the initial condition provided, or we can say given, initial condition which is VC 0 plus is given as 0 volt, and I 0 plus, which is initial condition for the current in the circuit, is given as V naught divided by R. Right, so what we're going to do is we are going to apply very simple steps. So there is 3 steps we need to follow, and once we complete that 3 steps, we can have our transient current analysis of our RC circuit. So let's go with this with step by step. So step 1. Step 1, we need to apply. So step 1 is to apply KVL in loop, right, of the circuit above, which is given in the circuit. So if you apply KVL stands for Kirchhoff's voltage law, which state that the sum of the voltage in a closed loop must be equal to 0. So if you look the circuit, that V naught should be equal to VR plus VC. And then we can further arrange this as V naught equals to, so VR is nothing but voltage is simply resistance times current, and the relationship for VC is given as 1 over C integration I dt, because the relationship of VC is written as 1 over C integration IC dt. Now, since the current going through the capacitor and current going through the resistor is same, which is I have represent this as I. You can see there as I here. So I haven't represent this as a IC. I have represent this as a I. Right. So next, what we're gonna do now, to simplify this, we have to differentiate on both sides. So let's differentiate on both sides. So differentiation on both sides. Okay, so if we differentiate on both sides, since your V naught is constant, so derivative of constant gonna be 0. And then we have R, which is a variable which goes in front, and then we have I. We're gonna get di over dt plus 1 over C, and that's integration will will cancel out with differentiation, and we're gonna get times I. However, since this is basically integration, and if we differentiate the integration, we are gonna get a constant. So the constant which C is given by basically VC 0 plus. And if you look the above condition, initial condition, which is VC 0 plus, is given as 0. So this value is 0. So that means value of C is 0. So what are we gonna get next? We're gonna get 0 equals to R di by dt plus 1 over C times I. Now do not get confused, because sometimes I'm representing I as IT, and sometimes I'm writing I as simply I, but that I and IT is same. Okay, so I'm gonna write here as a note. Remember, your IT and I is same. Okay, they are same in the expression. Right, so what we're going to do next, so this is our differential equation. So this is our differential equation, which we get after modeling our circuit which is given to us, which is RC circuit. So we can write there, this is first order differential equation for RC circuit. Okay, so that's the differential equation which we are looking at. Right, so after we got differential equation, we are going to go to the next step. So step 2 now. Now step 2 is to solve this differential equation. So we need to solve this differential equation. So let's write step 2 is to solve differential equation. Okay, differential equation. Now to solve this differential equation, there are many ways you can do that. You can use MATLAB, or you can use any classical method, or you can use Laplace method. So what we're going to do now here, we're going to apply Laplace method to solve differential equation. So we are going to solve this differential equation by using Laplace transform. So this LT refer for Laplace transform, and we will need some formula. So what I'm going to do here, I'm going to write the formula. Let's use blue color. So formula, I'm just going to write some formula which we will need to apply in our differential equation. So that's some formula I'm going to write. So Laplace transform, the first formula I'm going to write, I'm going to use this is a Laplace transform of derivative is simply yes IS minus I0 plus. Another formula I will need to use, which is Laplace transform of IT is simply IS. And another formula which I need to use is the constant, Laplace transform of constant. So any constant, if you apply Laplace transform on the constant, any value 1, 2, 3, whatever value you have, then you will gonna get constant divided by S. Okay, so let's use our differential equation then. So this is our differential equation. Okay, I will say equation 1 here. So let's use this differential equation, Laplace transform. So applying Laplace transfer in above equation 1 differential equation, we get, so what we're gonna get, so what is our differential equation? So we have r di over dt, okay, plus what we have 1 over r, sorry, 1 over c times I equals to 0. So let's apply Laplace transform first. Okay, let's apply Laplace transform, and same thing we can do for here as well. Let's apply Laplace transform. Let's make this clear. Let's go with Laplace transform. 1 over c times I equals to 0. Okay, so to or we can basically make our life easy to get rid of that r, but I think it's fine. So r is a constant, so we can move that around. So Laplace transform of derivative is going to be, so let's remove that r from, so we get r here, and then Laplace transform of derivative is yes, is minus I0. So let's use that. So we have yes is minus 0 plus. And similarly, we have Laplace transform of 1 over c times is. We're simply going to get 1 over c times capital Is. That's a frequency domain. Now Laplace transform time domain into frequency domain equals to 0. So let's make this more simpler. If we multiply, if we divide everywhere or every side, everything by r, then we're going to get yes is minus I0 plus 1 over rc times is equals to 0. So there is the initial condition which we need here. This is the initial condition. So what is the value of initial condition I0 plus? If you go up, the initial value of initial condition is basically V0 over R. So let's use that value. So we have yes is minus V0 over R plus 1 over RC times is equals to 0. Let's put this constant to other side, and we'll get yes is plus 1 over RC times is equals to V0 over R. So now we can see there that is here and is here is common. So we can take is common in this expression here. So we'll get is as a common, and the leftover is yes in this term, and then in this term we have 1 over rs or rc, 1 over rc equals to V0 over R. Now what we have to do, we have to throw this yes plus 1 over RC on other side, because we want to free our is on one side. So we're going to get is equals to V0 over R, everything divided by yes plus 1 over RC. Right, so this is our basically second step. So we are done with the second step. What we did in second step, we applied Laplace transform and find our transfer function. So this relationship is called transfer function, okay, in a frequency domain. Okay, this relationship is called transfer function. Okay, so we are done with our step 2. Now what we need to do for step 3? Now we are moving on to step 3. Step 3, we're going to apply inverse Laplace transform. So whatever expression we have got from transfer function in above equation in yes domain, we can apply inverse Laplace transform to convert back into time domain. Okay. Again, for that we need to know the formula. So let's write the formula for the inverse Laplace transform. I don't need to write the whole formula. I'm just going to write basically two formula which I will need to use. So the first formula I'll have to use is inverse Laplace. So you say L minus 1, that is called inverse Laplace, 1 over S plus A. So anything which you see like this, 1 over S plus A, you can represent this as a, if you apply inverse Laplace in this kind of structure, then you're going to get e power minus at. That's going to be exponential function of whatever a you got, but that's going to be negative t. Similarly, you have inverse Laplace. If you apply inverse Laplace in is, then you're going to get it. Okay, so this is two formula I have to use, so I'm just writing these two formula. So let's apply inverse Laplace in above equation. So we have inverse Laplace. So let's apply inverse Laplace transform, and let's mention the equation also. Equation 2. Remember, this equation 2 is a transfer function. So let's apply inverse Laplace transfer function in equation 2. So what are we going to get? Inverse Laplace for is, and then inverse Laplace for whole thing, which is v naught over r, whole thing divided by s plus 1 over rc. So if you look the formula, inverse of is is going to be it. So we'll get it here, or I, doesn't matter. And then you have inverse of the constant, that's the constant v naught over r. So it can go over outside v naught over r, so that's not going to affect. So leftover is 1. So inverse of 1 over s plus 1 over rc. So your a, the value of a here is going to be 1 over rc. So what you're going to get, this relationship, you're going to get e minus, in terms of r, in terms of a, in the formula we have 1 over rc. So it's going to be 1 over rc t. So that is our expression for the transient current analysis, right? We'll say equation 3. And we are done with the by 3 steps. So let me write this here, which is the transient current analysis solution of RC circuit.